All right, this video is on orbits. We'll start with Kepler's laws of planetary motion. So it was believed before Kepler that, okay, let's start from the beginning. The original model for the universe was that the Earth was at the center of the universe, and that all the planets, which a long time ago included the moon and the sun, um, orbited the Earth in perfect circular orbits. And so you would have the Earth here, and in perfect circular orbits was like, okay, that's not a circle, but was like Venus, and then I'm trying to make a perfect circle here. Let's see. There we go. Everything orbited the Earth in perfect circular orbits. Eventually, Copernicus comes around and says that the center of the universe is not the Earth, but it is that the sun is now the center of the universe, and that everything went around the sun in perfect circular orbits. And okay, that's not the center, but you get what I'm trying to show you. Something like that. Okay, Mercury, Venus, Earth, Mars. And the definition of planet um, kind of changed, or the classification of planets kind of changed over time. So that's with Copernicus. Okay, Kepler comes along, and Kepler's a mathematician. He looks at the data, which looked a bit tedious from what I've seen from it. And he figured out that the sun, for one, is not at the center of an orbit, but it's at a focus. So let me back up. Planets don't move in perfect circular orbits around the sun, they move in elliptical orbits. And okay, I drew this one kind of exaggerated, but the sun is not located here in the center of the orbit. It's located at a location called the focus. So this would be a focus, and there's two foci or two foci in an orbit, and the sun is found at one of them. So the sun can be here or it can be at the other one. Nothing is at the other one, but with an ellipse, mathematically it just has two foci. And let's say there's a planet, let's say it's Earth, and this is Earth. And so planets move around the sun in elliptical orbits with the sun at one focus. And that's what we call Kepler's first law. Well, let's just move on to Kepler's second law. An imaginary line drawn from the sun to a planet, we use purple, will sweep out equal areas in equal time. So suppose this is the Earth, and in 1 month, the Earth moves from here. Instead of drawing it from there, there we go. Earth moves from here to here. And an imaginary line drawn from the Earth to the sun sweeps out this area. What Kepler is saying is that in equal amounts of time, so this was 1 month, let's say, we're just supposing, that so like when Earth is over here and it's moving around the sun going this way, and we drew a line from the sun to the Earth, this line has to sweep out an equal amount of area. So look at this slice of the pie there, this elliptical pie. And in 1 month, it also needs to sweep out that area. And I'm going to try to guess as to where that is. Maybe that's point is, since it's further away, this needs to be a smaller sliver of this ellipse. Guessing I think that's too much. Maybe you're about right there. And so if this is also 1 month, as the Earth moves from here to here, Kepler's saying that this area is equal. Now I kind of study this and I kind of figure out how, vaguely how he did this. But right now I can't remember how he did this, even vaguely. Okay. So this is Kepler's second law. This area is equal to this area, provided that the Earth is moving in the same amount of time from here to here, here to here. And what that means is Earth travels a longer distance when it's closer to the sun than when it's further away from the sun. And so Earth must be moving faster when it is closer to the sun than when it is further away. That should make sense. That it's going faster because it covers more distance. Here it's going slower, it's covering less distance in the orbit. So even though Kepler's second law is stated this way, I kind of think of it as the speed of a planet changes as it orbits the sun. Faster when it is closer to the sun, slower when it is further away. Kepler's third law figured out this relationship that the average distance from the planet to the sun cubed over its period. T is period. That's how much time it takes to make one trip around the sun. For the Earth, that's a year. So r cubed over period squared is constant for all planets. But if you try to take like the moon, let's say, going around the Earth, so you take the average distance of the Earth to the moon and divided by the moon's period as it goes around the Earth, which, by the way, the moon's period is about 29 days. Um, it's not constant with the planets. It's only constant for the planets. So those are Kepler's three laws of motion. All right, let's keep going. We're going to talk about orbits with varying levels of, realism to them. Let's suppose, even though Kepler said that the orbits are elliptical, let's suppose that the orbits of the planets are circular, because then the math kind of works out a little bit nicely, kind of works out easier. And true, most of the planets are very close to circular orbits. The closest one is Venus, it's almost perfectly circular. And the one that's most elliptical is actually Mercury and all the other planets in between. The Earth is, again, very circular, very close to being perfectly circular. So, after Kepler came Newton, and Newton said the sum of forces of, let's say this is a planet going around the sun, so the sun is big M, the planet is little m. The planet moves, let's say, in a circular orbit with speed v, and it is a distance r from the sun. The sum of all forces on the planet in this little system we've shown is just the gravitational, um, universal gravitation, or the gravitational force is what I meant to say. And the acceleration of the planet, it's not speeding up. This is a constant speed in this circular orbit. This is a centripetal acceleration. One of the r's cancel, the little m cancels. And so the mass of the planet, so far with what we're doing, does not matter. We are left with g times the mass of the sun over r. The distance is equal to v squared. And so this is important. This relationship relates the speed of a planet, or the speed of an orbiting satellite, with the mass of that central body here over the distance between them, r. Now, for the homework, you will need to isolate v to figure out the speed of the planet. And so that would simply be v is square root capital G capital M over r. We will, it's apparent this year that getting that M confused, it's not little m, it's big M. So it's the mass of this body here, not this one, not the orbiting one. Okay, you can keep going with this. So G M over R equals V squared, but we know a relationship for V, and I should have written this down next. Let me move this down here. We know from our circular motion days that v is equal to 2 pi r over period. In other words, the distance, in this orbit, the distance of the orbit, which is 2 pi r over the period, over the time, distance over time. And so we can substitute this expression here into our equation from above. And we can see what this gives us. This gives us gm over r equals, let's multiply it all out. This is 2 squared, that's 4. Pi squared is pi squared. R squared is r squared. And then this is t times t, that's t squared. And, okay, if we add this r to this side, if we multiply both sides times r, this one cancels, and we get an r cubed there. Let's do it like that. This is gm is equal to 4 pi squared r cubed over t squared. And if we move this 4 pi squared to that side, if we divide both sides by that, we get gm is gm over 4 pi squared is equal to r cubed over t squared. And this should look familiar because we just talked about this. This is Kepler's third law. R cubed over t squared is constant. And he didn't know what this significance of this was, but Isaac Newton did. And the reason why it's constant is because every planet is orbiting the sun. That's capital M. Yeah, g is a constant, and 4 pi squared is constant. And so this value is constant for all the planets. It's not constant for like the moon going around the Earth, because then you would plug in here the mass of the Earth, and this number, that quantity, would not be constant with the planets. Okay. So this is our next relationship. And okay, this one is important. We'll say this is another relationship that's important here. On the AP test, you do need to know that planets actually move in elliptical orbits. And you need to know Kepler's 3 laws, in other words. And you need to know how to be able to derive these relationships boxed in. Okay, this one's not really derived, but you need to know that one. And you need to know how to derive this relationship here. On your homework, you'll need to calculate the period of a planet given, the mass of the star or whatever, the distance to the star. And so it might be useful to write this down, that 4 pi squared over gm, I'm flipping this fraction, is equal to t squared over r cubed. I flipped this side of it as well. And we'll just move the r cubed over here. This is 4 pi squared r cubed over gm is equal to t squared. But for your assignment, it might be more useful to write it like this, that this is 4 pi squared r cubed over gm is equal to t. And while I was doing the assignment, I kept forgetting what this equation was, so I kept deriving it over and over and over again. It's good practice for you to derive this expression or this equation, so you know how to do it, because you need to know how to do that anyway. So this first equation is a relationship between the mass of this body, the distance to that body, and v, so r, v, and m. This one is a relationship between v, period, and r. And this one is a relationship between m, period, and distance r. And that is for circular orbits. One thing to note here on the assignment, here, let's do it this way. Yeah, let's do it this way. So this is distance r, but let's say this is not the sun and this is a planet. Let's say this is a planet and this is a satellite orbiting the planet. Okay, same picture.
But with that, we can say this, that this would be the radius of the planet, capital R, and the satellite is orbiting above the surface of the planet, a distance h, the height above the planet. And so, if you figure out r and you know what the radius of the planet is, you can figure out the height above the planet that satellite is. You can just take little r minus big R. And really, you can do anything with that. You can add up r plus h to get little r, That's the relationship there. Let's do a quick example. I think I still have time. A rock orbits the sun, and let's change this. Let's just say the sun is 2 times 10 to the 30. You might also see it as 1.99 times 10 to the 30 at a distance of 1.5 times 10 to the 11 meters. So what is the velocity of the rock? And then what is the period of the rock? So velocity is 2 pi r over period, but we don't know period because we're looking for it in part B. So you can't use that one. But we do know a relationship between speed, mass of that body in the middle, and the distance to the body. This is square root of g m over r, which we derived on the previous page. So by the way, whenever you draw the square root symbol, make sure it goes all the way down to the bottom of your fraction, all the way to the end over here. This is 6.67 times 10 to the minus 11 times the mass of, in this case, the sun, over the distance to the sun, 1.5 times 10 to the 11. Cool. And so we'll just calculate that. Put in square root. Already forgot what it was, 1.5. That's the wrong page. Oh no, that's the wrong spot. 1.5 times 10 to the 11. Yeah, looks good to me. 29,821.7. Or 29,822. Mm-hmm. At such a fast speed, do you really need the 0.7, 21.7? Anyway, so that's the speed of the planet, of the rock. Next one is period. I totally did this the long way last time, so you can do it either way. V is equal to 2 pi r over t, and we can rearrange this equation for period. Period would be equal to 2 pi r over v. This is 2 pi times 1.5 times 10 to the 11 over v, which is 29822. So you could do it that way. But you can also do this one. This is t is equal to square root. See, I always forget what it is. 4 pi squared r cubed over gm. It's good to practice with this one, so let me move everything here over. This would be 4 pi squared 1.5 times 10 to the 11 cubed, and that square root sign needs to go all the way across, over 6.67 times 10 to the minus 11 times 2 times 10 to the 30. Yeah, let's do this one. Let's do this one. Well, we can do it both ways. This is 4 pi squared times 1.5 E11 over 6.67 E minus 11, or negative 11 times M, which is 2. I'm sorry, is it 2? Yeah, 2 times 10 to the 30. And I forgot to cube this. And the more times you practice, the less you will forget. Cool. 31603,766. That is in seconds. Let's do it this way. Let's see if this works too. So it should. Over the speed, 29822. Okay, comes out a little different. 31603,440. And that's probably because I rounded that speed. 31603. But it's only different in the later decimal, or the later places here. 440. Now, that's good. I'm going to use this one because this one I rounded. I know I didn't round here. So period is equal to 31603,766 seconds. But that's such a weird unit of weird unit to use for the period of a planet, or a rock in this case, orbiting the sun. So we're going to convert this into a unit that makes a little bit more sense. We're going to go from seconds to Earth days. And, oh gosh, what is it? 48600? Let's look this up. Or is it 86400? I forget. It's 864. 864 for 1 Earth day. So we can divide this number. I'm going to take this one, and we'll divide by 86400, and we get 365.8. Earth days, and of course this rock we're referring to is the Earth. So even though we didn't ask for it to be in Earth days, well, there might be a question that makes you convert from seconds, or convert from hours to seconds or something. All right. Let's keep going. Let's finish this up. So now let's go from circular orbits, which is kind of like an ideal, not an ideal, but like a simplified version of an orbit. Circular orbits are rare. It's mostly like man-made objects that go in circular orbits. Real orbits of celestial objects are elliptical. And so this is an ellipse. Here is the, let's say it's like a sun, or the sun, or, the object it's orbiting. And let's say this is a satellite or a planet that is orbiting this object here. So it's an elliptical orbit. Point A is a location that is closest to the sun. Point B is the furthest from the sun. When it comes to astronomy, we call this location the perihelion. If we're orbiting the sun, this is called the perihelion. If this is a satellite orbiting the moon, let's say, this is called perigee. The furthest point here is called, again, if you're orbiting the sun, this is called aphelion. If it's something orbiting some other object, this is just in general, it's called apogee. We know that it is moving fastest when it has point A, and it is moving slowest when it is at point B. And so VA, I'll do this in a different color, is greater than VB, which is the speed of the object at those points. The distance from the sun, let's say, to this object here, this planet, is RA, and the distance from the sun to that planet on this point, the aphelion, is RB. And the planet, the orbiting body, has mass little m. Of course, the sun there has capital M, more mass. So before we solve this problem here, we'll get to it. There's two quantities that are conserved in orbits. One is mechanical energy, which is, our relationship E1 equals E2, which is K plus UG is equal to K plus UG. We'll talk more about this in the next lesson. UG for astronomical, on an astronomical scale, is not equal to MGH anymore. And so we'll get into that in the next video. The other quantity that is conserved is angular momentum. For an object that's orbiting some other object here, the angular momentum is simply RmV. And so, question part A is really, what is the angular momentum of the planet? If we are given RA, RB, we are given VA, and mass little m, given those. Given the mass, the speed of the planet at that point, the distance to it at perihelion, and we're even given the distance to aphelion. And so for part A, we will calculate L. We can say the angular momentum at point A is the distance to A is RA, the mass of the satellite, times VA, the speed at that point. And that's it. These are all given quantities, RA, VA, M. Question B is, what is the speed at point B, which we are not given? Well, we can say the conservation of angular momentum. The angular momentum at point A is equal to the angular momentum at point B. So this is RA M VA equals RB M VB. And so to figure out VB, we can just, well, first of all, we can cancel an M, and then we can just divide an RB. Divide RB. So it turns out it is a ratio, RA over RB times VA is equal to VB. Or you can say RAVA over RB. By the way, if you're ever trying to figure out the speed of this planet here, angular momentum is your way to go. Much easier than doing this. And the reason is because UG, that equation is a little bit, what's the word? Unwieldy, let's say. It's a lot slower. Okay. And there we go. And I think that's it. Okay. We know about angular momentum at point A and point B. What about angular momentum at some other location? Let's call it C. At point C, the planet is moving, with speed vc, and the angular momentum at point C, we would think it's rc mvc, but it's not, because this is rc, this is vc. But when we did this equation, we had to have a perpendicular, this is perpendicular, where we have RA and VA is perpendicular. It's the distance from the kind of the axis of rotation to the object, to the line of action. Excuse me, sorry, I'm getting a little distracted here. So this one is not perpendicular, but let's suppose that we were given the angle, this angle here, theta. Well, essentially what we can do is, this is kind of like one way of looking at it, is looking at a component of VC. This would be VC sine theta. So this has never shown up on anything like AP, but that's kind of cool to know, that the angular momentum at point C is RCM VC sine theta. Cool. And then the last part I think we went over in the notes is actual orbits. We've been looking at really simplified orbits, like here is the sun and here is a planet that's orbiting, and we think of the planet as just orbiting. We can think of it as a circular orbit or an elliptical orbit, but this thing is moving. The sun is not moving. In reality, I didn't like my picture there. Here's the sun. And let's take Jupiter as an example. We'll make Jupiter brown. Here's Jupiter. Now, we say that Jupiter orbits the sun, but really, they both have a gravitational force, and so they both kind of orbit each other in a way, but it's really the center of mass. The center of mass between Jupiter and the sun, because the sun is so massive, I'm not drawing it to scale here, the center of mass is not in the center of the sun. It's a little bit off to this side here. It's somewhere inside the sun, but a little bit off center. And so Jupiter orbits that center of mass there, and the sun kind of orbits that center of mass, so it kind of wobbles in place. It's hard to draw it, but yeah, it kind of wobbles in place like that, very slightly. If you have two stars that are, similar mass, or the same mass, let's say, well, their center of mass is going to be somewhere actually in the center. And remember, over here, it's because the sun is so massive that that center of mass is closer to the sun. And it's actually inside the sun. So you might get something like this, which we call a binary system. And they kind of orbit. Terrible picture here, but they kind of orbit each other like this, let's say. Cool. And I think that's it for orbits. Remember, know how to derive especially this one and this one.